Hello everybody, welcome to Dr.K.Liu Maths channel. Some guys want me to talk about about the application of Hessian matrix. Here I look for several examples, found that is quite match my presentation topic, which is multiple variable calculus, finding the critical point of a function f bracket x y. Okay, before talking about the Hessian matrix, we have to talk about the critical point of a function fxy. For a function fxy in two variables, it means in 3D surface, it is a 3D surface. The critical point of the function is defined as the partial differentiation of fx with respect to x and y. Set these two partial differentiation into 0. Then those points, finding that those points are called critical point. Here is a critical point. Okay. Moreover, if we find that there is a lot exists for this point for the partial differentiation of fx, partial f1 f1x or 1 f1y. At that one, either one or both does not exist. Then this point are also called critical point. Combine critical point, we can divide critical point into three types of points. One is maximum, local minimum point, local maximum point. And if neither of them are called saddle points. Okay, and for to test which point is to belong to a maximum, minimum, or saddle, we have to use the second derivative test for critical point of function fxy. Please remember, it is only that for function fxy. Other case, we have to use Lagrange multiplier method. Okay, here we introduce the Hessian matrix. The Hessian matrix, it is a double partial differentiation, second partial differential equation for 1f, 1x, and 1f, 1y. If we further partial differentiate this one, we have partial square f, partial x square, this one. And then second, partial square f, partial x, partial y. Okay, and I think I write this one in this position. And for this partial differential about x, then we have partial square 1 square f, 1y, 1x. It is matched the rotation of this one. Okay, finally, partial differentiation of this one, partial derivative, 1 square f, 1y square. And we write this test, fxx, fyx, fxy, fyx, and fyy. It is called Hessian matrix. And for the Hessian matrix, if the determinant at the point for the point of critical point of fxc, if the determinant of the Hessian matrix is greater than 0 and second partial derivative of f with respect to x greater than 0, then that critical point is belong to local minimum. And if the Hessian determinant of Hessian matrix is greater than 0 and 1 square f, 1x square less than 0, then that point AB is a local maximum. It is quite similar to the case in the second derivative test for in one variable. Okay, and if the determinant of Hessian matrix is negative, then this AB is a settled point. Okay, we have divided this into 3 cases. For the last case, if the determinant of the Hessian matrix is 0, there is local conclusion. It means it may be local maximum, local minimum, or a settled point, but we don't know which type of point it actually has. Okay, there is a example. I think it is a simple example for fx equal to 16x plus 12y plus x squared plus y squared, and I draw the figure here. This is a curve of this function. Surface, it is sorry, it is I should emphasize it is surface in 3D, and I also draw the coordinates x-axis, y-axis, and z-axis. That point should be this one. Later I will calculate how to calculate this one. Okay, for the first step, we have to partial the derivative of this function with respect to x. Let me see. And 16 plus 2x and 1f, 1y. This should be 12 plus 2y. And set this into 0. For the first one, we have x equal to minus 8. For the second one, y is equal to negative 6. Then it is the critical point. It's negative 8, negative 6. And to determine that point, this point, that point belongs to, it may be local minimum, local maximum, or settled point. In this case, we have to calculate the Hessian matrix. Denoted by the Hessian matrix by x, fxx, fxy, fyx, fyy. Fxx differentiate with respect to x, this 2. And differentiate this function with respect to y, this 0. Let me see. Yeah, 0 is here. But anyway, it is also 0. And finally, differentiate this function with respect to y, this 2. And the Hessian matrix determinant equal to 4. And moreover, that point 1 square f1 x squared at the point negative 8, negative 6 is equal to, for any value, it is 2, greater than 0, greater than 0. Both Hessian matrix are greater than 0, and this also greater than 0, then that point is local minimum. Therefore, negative 8, negative 6 is a local minimum point. Okay, that is the result of here. But anyway, I hope guys can enjoy this video, and if you find Dr.K.Liu Math channel is useful, please subscribe my channel. Okay, bye bye.